So this week we were looking at chapter 10, batch processing. At the beginning of the chapter, they were kind of just giving us the overview. They were saying in the past, we've looked at kind of the typical relational setup. We've got requests, queries, responses, and results. And typically you think of these in terms of response time. So someone requests a bit of information, and then how long does it take for them to receive the information back that they wanted? But then in batch jobs, you have kind of a different metric. We don't really care about response time because we know it's going to take um, more than a user would typically wait for. It's not just milliseconds, it's much longer than that potentially. And so you typically measure it in terms of throughput. So like how much data can you actually chew through quickly? Um, and then they categorized the different kinds of systems into three different buckets. So they had services, which is kind of what I was talking about before. You have your request and response, and then batch processing, which is what we'll be talking about the most of the time today, and then stream processing, which is what we'll talk about in the next chapter. So they started us off with batch processing with Unix tools. So they basically said, um, they showed an example with parsing some logs. So we've got all of this output from some weblogs potentially, and we want to just grab the URLs out of those weblogs. And so they used various Unix commands, and then they said, okay, using this series of 7 different Unix commands, we can return the top 5 unique websites. So these are the most popular websites from your weblogs, basically. Um, and they showed that you can do it with the chained Unix commands, or you can also do it with a custom program that you write yourself. So they showed an example in Ruby, and in that basic example, they basically just had a hash map that stores the new URLs and then has a counter that increments with them. Um, so every time it encounters a new URL, it will add that to the hash map, and then it will increment its counter, and then um, it keeps that all in memory. And so one of the big distinctions they were making was eventually that Ruby program could run out of memory. It's not particularly likely, but if you have billions of URLs, for example, your program might create such a big hash map eventually that it just runs out. And so the Unix pipeline operates a little bit differently in that it's not just accumulating a whole bunch of stuff in memory. It's actually making use of the disk in certain aspects. Um, so that was kind of the distinction they were making there. Um, then they were talking about the Unix philosophy. And so they were listing kind of 4 core ones, saying make each program do one thing well instead of having it potentially do many different things with lots of different options. You just want it to um, do its one core thing, and then expect your output to become input. So like in those Unix commands, there's multiple layers to things. So it's going from one command to the next to the next. And so it has to be a consistent format that you can pass along. And then another concept was design and build to be tried early and iterate. So they were saying basically roll things out, prototype, try them out, see what works, and continue to improve over time. And then they said use tools to lighten a programming task. So there's a big focus on automation there. Um, they were mentioning Unix favors a common interface, so standard in and standard out, always ASCII. So in Ruby and stuff like that, you might have a dictionary or a hash map or various different types, but this is just always raw ASCII characters basically, and you can parse it however you like, but it doesn't really come structured. It's just as it is, which is kind of nice because it's flexible. You always have exactly the same thing, but it's not quite as user friendly necessarily. You might have to do additional work to get things in the format that you want. Um, Let me make this a little bit bigger. So then they started talking about MapReduce and distributed file systems. And so they were basically likening it to the Unix tools, but with the idea of spreading it across thousands of machines. And then they said it's built on HDFS, Hadoop Distributed File System, and it has that shared nothing principle that we've talked about a few different times in the previous chapters. So it's assumed that across the various different systems, they aren't actually sharing any information. Anything that they're doing is just specific to that one node. And then they mentioned that there's the central name node, and that keeps track of where the file blocks are stored. So you have your data that's split across all of the different systems, and then the central name node says, okay, this one over there has this bit of information, and this one over there has this other bit of information at the file block level, basically. And information is replicated across the different systems. So it's not just a single copy split across many systems. It might be multiple copies. And they mention a few different techniques for doing that. It might not necessarily be exact copies. It might be kind of striped in some way. Then they were talking about the MapReduce job execution. And they're saying it's basically a programming framework that's used to write code to process large data sets in distributed file systems. So you have your HDFS, and then you use MapReduce in order to crunch through that and figure out certain things about your data set, basically. The pieces of it, they kind of laid out 4 different directions. So they said you read a set of input files and you break it into records. So that's kind of that step in that weblog thing where it's basically you just have a raw string and then you want to actually break it into this section is the URL, for example. And then you call the mapper function and it will pull out the key and value. And then you want to sort those key value pairs by the key. And then it will send the keys to the different to the different systems running the reducer function, and that reducer function will iterate over the key value pairs. And so in theory, what should happen is common keys should all end up on the same system in that regime. And then they went into a little bit more detail about the mapper. So the mapper is called once for every record. It extracts the key and value. For each input, it can generate any number of value keys or key value pairs, even none potentially. So if it doesn't match a certain criteria, it can just basically stop it. And it's only given one record at a time. So it's not possible to do stuff across records. You only have the knowledge of the individual record you're given at any point. And so that's a little bit different than if you're used to having your whole thing in memory and then you're able to do various statistics and stuff on it. You just have to make the atomic unit the row that you have, which in sometimes can be a little bit confusing, and you have to think about things in a slightly different way. Then they talked about the reducer that collects all of the values from the same key and iterates over that collection. And then it can produce output records. And so in this case, it would be like the number of occurrences of the same URL. So in that first example, we had part of the function that would actually count the number of unique URLs. And so this is what the reducer would do. It could basically say, I've got this key. I know that this key occurs 35 times, and then it would just return 35 for that specific key. It's typically written in conventional programming language. So they were mentioning a few different ones. They said that the code for the mapper and reducer needs to be sent to all of the different systems. So you have 10,000 different systems, you write some code, and then your code gets sent to all of the different systems with the mapper and the reducer, and then they're able to run it on the data that they have available to them, their certain file block. Then they mentioned the shuffle procedure. I'm not sure I totally understand that bit. I don't know if anyone's able to fill in that blank potentially.
I can't remember.
So-
Winnie, have you talked about using, or was that Chris? Were you about to say something?
Yeah, I was got to say the problem that you end up with usual mappers is that you don't always end up with the data that you need to interact with in the same place. And so what will happen is you'll kind of look at some of it and shuffle it all together to try to figure out, is this the data that I need for these pieces? So trying to think of like a good example, like if you have a bunch of group by operations where you're like, oh, okay, show me all of the stuff that is sorted by country, or not sorted, but like aggregated by country. In a lot of, some of the cases that will just go through multiple mapper iterations and reducer iterations. But in other cases, it's like, well, for this to be optimal in this setup, I really need these countries lumped together on this place where I'm doing processing. So that's where a lot of the shuffling happens.
Hmm.
Do you know, in traditional MapReduce, is there sort of another way to move things around other than MapReduce? Like, are there jobs that just simply go straight to the file system and say, move these pieces around or something like that?
In a traditional Hadoop architecture, you mean?
Yeah.
So the Hadoop that I used, the query would go hit that main head node, and then it would get parsed and broadcast out in a broadcast message to all the nodes that are within. I mean, in our cluster we had 1,024 nodes, and the broadcast was a broadcast message that went out to all 1,024 nodes. Basically, all the nodes received that query, evaluated that query, and either retrieve the data itself, and if it could, it would then package that data up and send it back up to the head node. But as you could tell, not every node may return a value. So at some timeout, the head node would say, "Okay, I got all the data." So if one of the data nodes would receive the request, it would start the query. If the query had a timeout attached to it of 1, 2, or 3 seconds, and if the query didn't find anything within that, it just quit. The process would just be thrown away. And then the data would come back, get sorted into its, and that was basically the shuffle process, and filtered again if there was additional data requirements, and then sorted in ranking, and then passed back to where the query source was. But as far as the replication is concerned, we replicated our data center in thirds. So we had 3 replicas across of everything that we crawled, because we were a search engine.
Yeah, I guess the thing that I was wondering is, let's say you've got files and you've got, I'm just making something up, files that are, per server, per day, per business unit, right? So if it were just one thing, then you could easily just run a MapReduce job to, like, group it by date instead of grouping it by server or something like that. But when you have multiple keys and stuff, if you just, without having to do this heavy-handed MapReduce, if you just simply said, oh, like, all of server A is on this one node, all of server B is on this other node, but really what I want to do is I want to rearrange them so that all of Monday is on one node and all of Tuesday is on another node.
Well, when you ingest data into a Hadoop, you don't care. You want because you're going to get better response spreading everything out. Okay, it really is. You get better performance if you take your data sets and make it spread out as wide as possible. So each node, when a query hits it, is querying less data, right? So if you put all of Monday's data then on one server, then the one server is only going to answer the query. But if you take that same data and spread it across 20 nodes, and it's a smaller amount of data on each node, you can query that data faster because you're doing it in parallel. Does that make sense?
Yeah, I guess maybe I'm getting a little bit ahead, because it's good for the MapReduce until you hit the first join you have to do.
Yes, that it is true. And there is, I mean, you got the other one you got to remember, and for those of you who've never used it before, MapReduce is great for metadata. It's great for the internet because that's what it was really designed to do, is parse web pages. But the ranking and everything else is by keyword that's found in the documents that you're ranking. So if you've got images, then you can't rank an image. You can only rank the metadata that's attached to the image. So Hadoop using graphic images doesn't work very well, but it works great on the metadata. So if you could store the images separately, but extract the metadata and put that in a MapReduce, then you can take advantage of it. So the data structure and the data type matters.
And I would say along those lines, your query matters too. So yeah. to your example, Ted, where you're like, oh, let's put all of Monday on this server and all of Tuesday on this server, versus let's put all of server A on this server and server B on the server. If you're looking at just data by the day, that falls into this pattern where you are getting a hotspot in one server. But if you're saying, show me all of the data for last year, aggregated by day, or something, then that pattern might match for what you're talking about. So there is a lot of times where it's like, you'll do some raw loading of your data in, and there are times when you're like, no, we're going to be hitting this data over and over again, asking different queries that are all of a similar format. So we need to repartition it in this way to get it redistributed in a way that's efficient for these queries. So sometimes you'll get duplicate data because you're like, well, here I need to look at it by server, and here I need to look at it by day. And it really doesn't make sense to try to do a server day combo. You're just breaking it out, in those different patterns. So there's a lot of work in ETL that is trying to follow that pattern. And it really just comes down to how fast do you need an answer? How often are you doing the query? Does it make sense to repartition? Or, all these things come into play.
Thanks, Chris. Yeah, and I think that if there's a short answer to it, what I was looking for is that repartitioning, you wouldn't necessarily use MapReduce for it. You would use an ETL tool or something else.
I mean,
right.
To that point, you can use Hadoop to repartition, right? Because in a lot of ways, if you're repartitioning, okay, maybe you're doing let me load everything from this server and distribute it out. Well, if it's already on that server, you're already stuck, right? In other ways, it's like, oh, let me take this huge thing that's spread across all these servers and let me spread it in a different way because I need a different aggregate. We're still gaining all of that power of the distributed computing without necessarily having to unload all your data to a secondary store or to reload it from your original store in a different manner. So again, it's kind of situational. People like different tools, and some will just do it in the same situation.
Cool, thanks.
Yeah, I think one of the example I can think of using repartitioning is when you loaded several days of data and then you group by dates, but then like after you group by days, you do some aggregates. Some days have more data, some days have less data, and then you need to do another aggregate on top of these things. Then you might want to repartition those things during your the second part of the job, and such that it speeds up the computation. Otherwise, you might have one executor stuck in a large amount of data while the other ones finish pretty quickly. Yeah.
Thanks, Winnie.
And then I just have one side comment from my recent work stuff. My teammate on my group is trying to run a PySpark job, And then in the notes earlier, it mentions that like the MapReduce system will copy the code over to each of the node to run the job, right? But then but this particular PySpark job, we need certain packages to run the code. But then like on the main node, you can pass the environment in, but then like on the other nodes, they don't have the Python environment to run these packages. So the code couldn't run when we were trying to process a PySpark job. So that's one of the painful things when you don't when you think about how to set up your system to run these jobs. Yeah.
Thank you. You answered my question.
Oh, what was your question?
Technically, how it speeds up aggregation.
Okay.
The shuffling, how it is helpful, the shuffling and repartition.
So have you heard of a technology called SPAC? Winnie?
Stack? S-T-A-C-K?
SPAC, S-P-A-C-K.
Oh no, what is that?
Oh, so in the type of, it came out of Stanford Linear Labs, and it's been gaining popular use over the last 10 years. It allows you to quickly load up a specific environment. Not unlike Python has its own environments, but this is, so you can go into your job stream for either a Torque job or PBS Pro or Slurm job or one of the other schedulers out there. But what you do is you load up SPAC, and in SPAC you could say, I need OpenMPI, this version 3.14. I need a certain math kernel library, or I need certain Python libraries. You can call out the specifications, and the SPAC, basically the SPAC maintains a collection library that's available for the cluster. And then when the job runs, it loads up those elements that you need before the job starts. So it basically sets up an environment. That way you don't, in HPC 20 years ago, you basically would configure specific nodes to work a certain job type or job stream. And so you'd have fat nodes, thin nodes, you'd have large memory nodes, you'd have nodes that have spare disks and stuff like that. And then, but all the libraries installed would be installed for that image for that job, and it could only run jobs on it. SPAC removes that dependency, so you could basically build your environment as you go, as the job executes, and then unload it when the job finishes. But again, it's very powerful. We use it on our clusters, and it comes in handy, and it'll help you with that, where you submit a job and you got nodes that are in the environment that don't have what you need. If you have access to a common SPAC library, they can load that stuff dynamically and then unload it when it's done.
So does it assume that I have the permission to install things on the cluster on like?
Well, this goes from if you're a systems administrator and managing the HPC space versus the consumers, the scientists who are working in the space. Like in my roles, I've been the sysadmin for a lot of these environments. So normally the sysadmin would set up its SPAC, set up the library so you can load the libraries as needed and call it, and then you turn it over to the consumer base, the scientist base, and say, look, if you need OpenMPI, these are the versions that you can choose from. If you need a math kernel library from Intel, if you need some other other installable libraries or whatever the libraries you were, and you would install that into a common node. And then each compute node is thinned out to be just a compute node, so it could be available to anybody. And then as the job streams run, they'll go up and load up the resources they need and access to the libraries. And SPAC will fix the pathing and fix the LD library calls so everything is properly available. some codes may require Python 3.1 or 2.7 or 3.6, and that helps with that environment too, because you can load up the environments that you were specifically looking for. Again, it's SPAC and it's available out of Stanford Limited Library. And if your environment doesn't have it available, then I would basically hit your sysadmin team and say, hey, get it for me.
I don't know how many meetings would to do
so
it,
if I
but
may,
it looks pretty powerful though.
Yeah. So
Thanks.
if I may, Winnie, I don't think this is going to solve your problem if you're specifically running on Spark, because in the Spark environment, what's happening is ultimately all the executors are running in the JVM on the nodes, and the penalty you're paying is that PySpark turns all the APIs under the hood into Java code. When you want to use a Python library, it then has to load Python, spin it up, load your packages, and execute the Python code like as a function call. And then it has to basically serialize it and return it to the JVM. So you pay this huge performance penalty for using it. It's not that you can't do it. It's just this massive performance penalty so that pretty much nobody wants to do it. So if your library were written in Java, you would have none of these issues because you would just be able to bring it right into the JVM where the executors are already running.
Yeah, I think the lesson learned was just write everything in Scala, compile it, and get it to go.
Yes,
Yeah.
but if you want to use
that's the quick solution. But if
you want to use somebody's
run
Python
PySpark,
library,
it just takes extra pains. Yeah.
Right. If you just like a particular library that somebody already wrote and it's in Python, then unfortunately for Spark you have that barrier.
Thanks. I think the discussion is really helpful for me to tackle.
Yeah, I mean, I would still have a conversation with your sysadmins and find out what they're doing for you, because with the company I'm currently consulting with that's in Japan, we have 4 different customers using our clusters there. And when you look at the workloads, one is in manufacturing, who's doing a lot of fluid dynamics and other engineering works. I've got another group that's doing genomics research, and those configurations are totally different. But at the end of the day, they're still using an Intel cluster. One of the other customers is doing it's high resolution microscopy images, and all their code is Java based, and that environment is horribly complex, right? And we've built for them a Jupyter environment that is pre-configured. So when they log in, their environments get initiated, and all their libraries, all the Java tools they need are available to them, and they can just do their work. And they have PySpark there too. But again, it's that when they log in, their environment is created for them to do their work. It's basically pre-configured. And it took us, a couple of weeks to get those environments correct for them to make sure they're doing what we have everything they needed to gain access to the cluster and the data sets they need. But once it's done, they're clear to do all the work they want to do. So.
Cool. I will try contacting the system administrator to see what happens.
Well, thanks for the discussion. That's definitely valuable. Lots of new information. So going back to the book, they started talking about joins a little bit. So you have a record of information and you want to associate it with some other record. In a relational database, you typically have your foreign key, and then you can just do a join off of that. And so in a relational database, you might use an index, but In MapReduce, you're always forced to do a full table scan, which is a lot more expensive. And so they were saying that it only really makes sense to do the MapReduce job when you're actually doing it across many users. If you're doing it across the whole distributed file system, it doesn't really make sense if you're just looking for a single user. That use case doesn't make quite as much sense because you're doing such a expensive task because you're forced to do the full table scan. And so they laid out this example saying, what happens if we want to associate some user activity with some user ID? And so they laid out one scenario saying, what happens if we try to take this user ID info and then look up the activity throughout the process. So say I have this user ID, I go to the database, I say, find me the user activity for this ID. And that can end up just being exceptionally slow because you're making a request for every single ID from the database. And it's just a lot of back and forth between the network and the amount of requests and everything like that. And so they're saying that you have to promote as much locality as possible. You want the most things on the same nodes as you can. And so what they were saying is it's better to basically put a backup of the database inside of your file system and then to just query through that. I'm not exactly sure how that would work in practice because I haven't messed enough with HDFS and MapReduce, but that's their recommendation there. Then they were talking about sort merge joins. And so the way the things are sorted, it can make it so the reducer always sees records for the user DB that's followed by the activity events in time order. And so they're calling that a secondary sort. So basically the first one it would see would be potentially the date of birth. And then after that, it could be all of the different activities. So it could be, here's their date of birth, here's where they visited this URL and that URL, and then it can basically store the first bit of information and then take the difference between all of the later bits of information. So the reducer actually does have some tiny bit of state there, just the one bit of information that it's caching. Whereas the mapper is always just purely looking at a single row at a time. And then they talked about the group by operation. And so they're saying that the simplest way to do that is to have the mapper just emit the key value pairs with the groups that you want to be the keys, basically. And then they talked about handling skew. And so this is something we're kind of talking about. If you have your data not evenly distributed, if one ID in particular has millions of examples or something like that, then one machine that is doing the reduce job might do a massive amount of work in comparison to another one that's hardly doing any work. And because of the way MapReduce is structured, you need the entire job to be finished before you can actually get any useful output and continue on to new jobs. And so they talked about there's various different tools in order to fight that, because you don't want your entire system to be bottlenecked because you have one ID that has millions of records, and then you end up just waiting on that one node constantly because it's the only one that can handle that specific thing. Then they talked about the map side joins, and they said if you can make assumptions about your input data, it can make the joins faster. And so they're saying your mapper takes one input file and creates one output file. And they mentioned broadcast hash joins. And so they're saying that this works when you have one large data set that you're merging with one small data set. And so it might be possible for you to just fit the entire small data set in memory and then just be doing that merge on the fly when you're doing your map and reduce. You just have it in memory, and then you can basically pair the two together as you're going through the whole file system. they're mentioning that it's also possible to put it on disk potentially. So if you have something that's too big to fit in memory, you can put it in disk. Like most of the other things, I don't have enough hands-on experience to say exactly how that would work out, but it is something that they mention is possible. And then they mentioned the partition hash joins, which is kind of what I think, Ted, you were talking about before. If you organize things by day or something like that, then you're kind of skipping the first MapReduce step by just having it already exist on the specific systems. And so it might be a way of kind of shortcutting that by just automatically having it organized in such a way. But I think that in theory, you could just have an additional MapReduce job that comes before the other one, and that would be kind of equivalent as actually partitioning it that way in the beginning.
Equivalent semantically, but to the point, it depends on what you're trying to optimize for.
Mm. Yeah.
Right. It's a shortcut, but it happens a lot in my experience where people pre-optimize. Yeah, I mean, my main question is just if you were somebody doing MapReduce, would you spend all your day writing MapReduce jobs, or would you sometimes drop into some other tool, some other language, and move around data using something else? Or would you just basically live in your MapReduce world as the exclusive way that you move things around? Because you clearly can. I just didn't know if performance-wise it was faster to use other tools sometimes.
So you raise an interesting question, Ted. I had a couple of customers a little over 10 years ago. They were ingesting Medicare data, and this was all anonymous Medicare data. And they took all the comment fields, all the doctor's notes from the medical records, and MapReduced all of that into a Hadoop farm, took all the other, because you think about a medical record, right? In the medical record, you got a whole lot of fixed fields that had to do with dates and times and drugs and everything, and policies or procedures that were performed, everything else. Then they had all the comment stuff, right? So this customer, they ingested everything, parsed it out. So all the data fields that would typically be found that are fixed and locked, they all went into, basically fed into a Oracle database. But all the descriptions, all the comments and everything else, and all the doctor's notes, and the as well as the gotta think about the right term in the medical term, the codes for the procedure codes, and those descriptions went into Hadoop. So, and the Hadoop had links back to where the data records were in the Oracle database. So you could literally walk into an environment and query. You had access to the Oracle, so you could query the Oracle. But if you wanted to query on a keyword, you would go off to the Hadoop and come back and return you a large collection of medical record numbers that they can go evaluate and look into detail to get the rest of the data. So at the end of the day, you're still parsing that up front as to where the most value would be returned from. And that's what they were doing because they were looking for Medicare fraud. So just very interesting use case.
I was going to say that the majority of engineers that we have who are working in any of the MapReduce data lake partition space are going to use the same tool. So for our case, it's a lot of Spark and PySpark stuff. When they're moving data around within that space, right? Before it gets there, that's where I see a lot more tools that interact with it in a different way. So we have some data reading from, say Kafka and being loaded into
data lakes. This can be done in Spark. But just given the way it's coming in, how Spark is doing the partitioning, how Kafka is doing its partitioning, and like what we need to land where, and what, like there's some windowing on duplicate checks and a lot of stuff like that. That actually is a custom app that just writes stuff in. So different phase there. We got some other stuff that's using like Ab Initio, and it's like looking at a different, it's reading, again, data coming in and moving it into what their data storage is, because there are other data storage formats. Snowflake is kind of a popular SaaS one at this point, stuff like that. So I think it really depends on where your comfort zone is, and people are just going to largely stick with their comfort zones.
Thanks, Chris.
So after that, they were talking about the output of the batch workflow. So we've kind of talked about what you do, but they haven't talked about necessarily why you would want to do things like this. And so they started saying that it's somewhere in between transaction processing and analytics. It's not really either of those things, but it's closer to analytics. And so they were kind of pointing to the use case of building search indexes at Google. So they're crunching through a whole bunch of web pages, and they're trying to map to them basically, and they have this massive pool of data, and so they want to update their indexes periodically. So someone types in a search, and then it has to match to the set of documents that are related to it, and they need to update that periodically, and that would be a MapReduce job. One of the things they were mentioning is if you want to output this, one of the things they were kind of warning against is it might be, you might fall into the trap of you're running your MapReduce job and you want to just update a database. So you just have it so that on the reduce end, every time it finishes something, it just outputs a write to a database, and they recommend against this because it's going to be just throwing so many writes into your database is probably going to bog things down. But then there's also problems with if your job fails mid-run, then all of a sudden the database that you were throwing all of the writes into has a bunch of data, but you don't necessarily know exactly which has been written, which hasn't been written, and what stage it exactly failed in. So they recommend against that, and they basically say just write a new database inside of your HDFS, and then once the entire job is done, then just kind of export that database for it to be queried externally. So just don't directly write into an existing database. They mention similar principles to Unix. You want to treat your inputs as immutable. They're always going to be the same. And then you want your outputs to be expected to become an input at some point. So you run one job and it has to be in a format that's useful for a next job potentially. And they also mentioned one of the benefits is that it's easy to roll back mistakes. So if you run a job and you realize that you did something wrong or it fails or for whatever reason, you can pretty easily just say, oh, I have this old version. I'm just going to run the old code on the data, and then it should work fine. And you can just overwrite or write a new file or do whatever you want there. And it shouldn't be hard to do. And that's much harder if you're doing it on a relational database, because you've now written new data to the thing, and it's much harder to do a rollback probably. Then they're comparing Hadoop to distributed databases. And so they're saying that it's more like a on-read schema. So something we've talked about in the past is you're kind of just dumping the data in there, and then when you're actually pulling it out is when you apply this schema and you say, okay, this is this field and this is that other field. And it's pretty useful because the data is just in the raw format. They mentioned the sushi principle. You just put it in there, and then whatever you want, you can make using that. And so it gives good flexibility. If multiple different teams are looking at it, then you just have the raw data, and then the formatting is actually happening on the way out rather than on the way in. And I thought it was kind of interesting. They were saying that the fault tolerance that's built in here isn't necessarily because the machines were unreliable, but because at Google, they would lose priority to other higher priority tasks. And so they would just basically kill certain systems that were in the Hadoop cluster and just basically say the systems are going offline because they lost priority, not because they crashed or a hard drive failed or anything like that. Then next section, going beyond MapReduce. And so they were saying it's pretty difficult to write these jobs. It's definitely possible, but people have started making additional tools on top of that. So Pig, Hive, and Crunch, and Cascading are the ones that they listed off. And I've heard these mentioned. I've never actually used them, but I know that it kind of abstracts some things away so that you don't have to get as much in the weeds. Then they talked about the materialization of intermediate steps. So they were pointing back to the original Unix example. You have that 7 series of commands, and they're all piped into each other, and then you get the one output. And they were saying basically MapReduce has this disadvantage where one job has to complete before the next one is started. And so that can potentially slow things down. It can make certain operations redundant. And so there are various different tools they pointed out that can try to resolve that in various different ways. So they listed off Spark and Tez and Flink. And so one of the downsides they mentioned is that without materialization, so some of those tools try to skip various pieces of that, you might lose a little bit of fault tolerance. So if you're not writing all of the intermediate states, and then something fails, then you might have to go back and actually do all of the steps again, rather than just being able to start from the last job that was completed. But they pointed out that materialization might not always be strictly necessary. There's pros and cons there.
So by the way, Ryan, I also thought that comment about getting preempted for higher priority interactive jobs or whatever was revealing. I mean, I didn't really realize that. If you think about it now, I mean, people only run on dedicated clusters, and Spark, not only is it not sharing with other whatever interactive processing, but it won't even share nodes across Spark jobs. When you allocate a node to part of your Spark cluster, you get it 100%. You don't even share it with other Spark jobs. So if you have a node that doesn't need a lot of memory, it doesn't matter. It's just wasting it. It's completely dedicated.
Yeah. I thought that was interesting because when I had originally learned about MapReduce, I was told that was the reason that it was even created, was because of the fault tolerance across many systems being eventually to the point that you just know that there's going to be a failure. But it sounds like that wasn't necessarily the motivation. It was just because of Google's architecture and the way they prioritize things. So moving on to the graphs and iterative processing section. So they're pointing out you can store graphs inside of a distributed file system, but it makes certain jobs kind of awkward. And so they were pointing out that a lot of different graph algorithms might require repeated reads and operations in order to reach convergence. And so they were saying, well, one way you can solve this is you can basically just write a MapReduce job that is one step in that process, and then just have some sort of supervisor say, okay, keep redoing this same job until you reach some certain convergence condition. But in the setup where they have to do the full table scan, that might be inefficient because certain edges of the graph might have already converged and others might not have. So doing the full entire read might just be inefficient. And so they pointed out various different tools. I wasn't sure if this is pronounced Pregel, Pregel, something like that. But they pointed out a few different tools that were meant to try to reduce that in various different ways, and prevent the redundancy and repeated operations. Then in the last section, they were talking about the high-level APIs and languages, and they're saying that things are sort of moving in the direction of more declarative query languages. So right now you have to write your own map and you have to write your own reduce, and it's in whatever programming language, but it would be nice if eventually they could get to a fairly general, flexible setup where you just start doing a sort of SQL type thing where you say, here's my query and just do the thing. But the problem with that is right now, the MapReduce jobs have a whole ton of flexibility because it's just whatever program you write. It can do all sorts of custom things. And so declarative query languages might be nice in terms of the ease of use because you just say run this operation or do this other thing, but then you can't do the more custom stuff. So they're operating somewhere on that continuum, basically. And on top of that, people have been creating various different libraries that are helpful for that kind of stuff. So people have written stuff for k-nearest neighbors and various text operations and stuff like that. So you could just pull from these libraries and then plug it into your MapReduce job, and you don't have to write the whole thing yourself, potentially. So that's it for chapter 10. I don't know if anyone has any pending questions, comments.
I have a general question for you guys. Like, I know, I understand, like in your day-to-day job, you probably don't deal with this, or do you? Do you guys deal with this to the large extent? Like when you do data science work?
I don't. I think that this would fall a lot more on the data engineer side of things.
Mm-hmm.
A lot of this stuff is fairly, some of it is completely new to me. Some of it I've had minimal exposure to just because I've taken random classes, but I would say that I don't do any of this on my day-to-day, but it just depends on exactly what your job title is.
Mm-hmm. So from
I'd say,
go ahead.
So I was just going to say, some of this is also abstracted. So we talk about the high-level language, high-level APIs and language. I feel like this part of the book is a little outdated, but by a little outdated, we're talking like maybe 3 or 4 years. So time flies, right? Because there are a lot of things, there is the Spark SQL interface among others where there is like a declarative way, and it builds a computation graph and so it very much is a declarative model for that I think is in heavy use. And then a lot of libraries are built on top of that. Like there's MLeap, I can't remember, which is basically a Spark. It has hooks into the Spark library where you can do distributed machine learning training algorithms and whatnot. So I haven't seen it a whole lot, but I mean, it is to the point where like there's stuff that's happening where there's a bunch of stuff being translated to one layer, being translated to another, eventually being translated to a MapReduce job or set of jobs. You just never see it directly.
So Chris, in general, how do you keep up with all these new tools and what each one is doing and how the transitions are happening in the industry? I'm just very curious.
I don't have a great answer. I just try to keep an ear to the ground on what's going on. You know, seeing there's going, like, a lot of conferences have moved online, so I watch conference videos. There's the meetup stuff like this that happens. Like, I don't have an answer. I don't feel like I keep up, but yeah. So Becky, I would say that if you're not, you know, planning to be a data engineer, you don't need to know that much detail about these things, right? So you probably could just read Gartner reports and see which companies are the new rising stars. And so there's maybe on any given year 3 companies that you're like, maybe I want to know if there's a reason why these companies are becoming really popular. You know?
Right.
So like at one point, Spark started to basically like eat MapReduce, you know, and it became the dominant thing, right?
Right, but then that's probably a question that you can help me with. Even though I mean, it's not my job at all to delve into this, but it is always a question like what kind of systems that we have as a company and how, whether or not you need to make a decision to say, okay, spend the money to upgrade or change to a different system. So I imagine that you probably are also facing some of these decisions. So how would you approach it? Like, yeah, like Hadoop and MapReduce, I've heard my team talking about it like 10 or 15 years ago, right? And then less so in other companies these days. So, yeah.
Well, sorry,
Go
ahead,
Chris.
Ted. You first. Okay. I was just going to say, like, a lot of these things, you know, again, like we talk about MapReduce here. MapReduce is a technique more so than a particular software or technology. It's implemented in a wide variety of things. So if you hear people talking about MapReduce, they're kind of maybe, you know, using it in little m, little r kind of, you know, definition, where it's just like a general statement of the technique. Versus like something, you know, a little more specific implementation wise, like Hadoop and whatnot. So from the standpoint of like, it's really about figuring out what level people are operating at and what tools are enabling that. So we, you know, we're looking at a bunch of stuff about like, you know, what would be a better operating environment for people to be on, like some of the AWS stuff or some of the SaaS stuff and whatnot. And it's really just like, hey, you know, you take your, you know, your data scientists, your data engineers, they interface with one level of the environment, and you get opinions from them as to is it good, bad, or other. And then you take, you know, if there's anyone who's going to be managing it as a platform kind of level, your traditional operational items, and say, okay, how hard is this to run? And then you do a comparison based on their, you know, their results, you know, what they say about each of those levels, what the benefits are at the feature level, how much of a cost it is, and then compare that to whatever existing systems you have when you can do those bake-offs.
Gotcha.
Yeah, so what I was going to say is at the higher level, for me, for example, big data was a really big buzzword, and it's come down a lot in terms of people don't talk about big data nearly as much anymore. That's my experience. So I may be a little bit biased because I don't work in e-commerce, I don't work in social media. But so for me, 99% of what my company does, if we do an analysis daily, that's like good enough, you know, and we are not delivering analyses in real time. So if you're, you know, Wayfair and you have a recommendation engine, somebody types couch, you need to feed that back in, you know, sub-second response times. So there's a whole set of problems that those kinds of companies are trying to solve. For my company, it's kind of like, yeah, I think we probably want some kind of tool to help manage our data, have a more friendly data warehouse, easier to maintain, less engineers, hours moving data in and out. So like I talked to my boss, like maybe we should look at Snowflake or something like that. But other than that, the good news is that machines are fast and cloud stuff just kind of works without you having to know how it works, and the disks are distributed and redundant and they're fast. And so like, I don't know what your company does, but if you don't have users, thousands, millions of users that are like in real time, they need to see something where they type something and they get something back instantly. You don't necessarily need a lot of fancy tools.
Right. And I keep coming into that that kind of a situation where I still find it very hard for me to, I don't know why, articulate what my company does. But I don't know if you guys have also run into more of the situation where you have to connect different types of data, right? So like Ted, you're I think that your primary area is the medical data or your industry data. But then we have a situation where we actually need to connect like consumers, e-commerce data, their digital collection data, their survey data, and then their geolocation data. So do you guys ever feel or ever have a situation where that kind of thing also influencing really the kind of the performance and how you think about your data structure or your kind of data systems and all of that? Or is it more a matter of volume and speed that's required? But I'm finding that like trying to match or trying to join all these different sources of data is in itself is causing like that kind of performance issues.
So I'll give you a quick answer and then we can see what other people say. So for us, the data that we're using today, all of it is in-house. So whether we generated it or we bought it, it's all sitting somewhere on a disk. We don't have to go and call some API to get like the consumer data on person 1, 2, 3, 4, 5, right? It's all just sitting there in a pile. So even though like I have databases with, I don't know, 1 trillion medical claims, I don't actually consider that big these days. So yeah, we always complain certain things take hours, even sometimes more than a day to run, and other things user will want some report and it takes 10 minutes to run. So people complain about that, but like fundamentally, it's not really, in my world, a real deal breaker in terms of technologies. I don't know what other people experience.
So we have a combination of stuff. We do have data we need to merge from different places, but we usually, and I guess kind of taking a step back, there's 2 parts. There's what we have online and what we're serving to people. And then there's what our user, and then there's the ones that do the big number crunching. I keep calling it data analysis, but that's where our machine, and that's where our learning models are and everything. So lump all of that together, and that's what that is. And these are 2 very different parts of the house, from the standpoint of what technologies are in use and then what expectations are. So like we'll have training jobs that run, once a day, and they run for 6 hours, and they update 100 million records and then push that out to our online services. And so they're like, hey, now we need to do different recommendations. Okay, well, we'll check those million updates, and when somebody comes in, it does a lookup then versus having to push all that at the same time. So there's 2 different sides to the house and 2 different technology bases. And then
as for getting data merged in from other places, what we do is we have effectively a fairly common format internally as for where the data is stored and what format it's stored in.
Mhm.
And then we get some, like partners or gives us feeds of stuff. We have jobs that receive those feeds, process them, and put them into our data store in the format that we're looking for. So a lot of it, even within the realm of the data analysis, big data stuff, is about doing some pre-computations, and it'll be once a day this feed comes in, or maybe we get some streaming feeds. We do get a lot of telemetry data in as well, but those come in through the streaming pipeline and then get appended to our standard lake format. So
Chris, would you be okay to share what's your system on the merging side and ingesting side versus the other side of the house for data training and modeling?
I mean, the majority of stuff is operating, like our stuff that's operating on our data lakes, either going into it or coming out of it, is something that's Spark based for the most part.
Gotcha.
As I said, like we have some stuff depending on the case, like Kafka feeds into it where there's some variances, but for the most part, stuff at this point is all Spark or some interface to Spark.
Gotcha.
Very
Becky,
helpful. Whenever
thank you
I
guys.
hear that you're merging different types of data, I mean, that instantly brings, the concept of a data lake to mind. And so at a previous company, we would get, again, it's in the medical field, like TED, but we would get information from, like, for example, immunization registries. And it was in a very different format from, let's say, medical visits, which was in a CSV format, which was in a different format to immunizations, for example, which was in an HL7 format, et cetera, et cetera. And effectively what we ended up doing without acknowledging it was piecemeal, because this was a startup, we built our own data lake effectively, right? Where we were just throwing all this stuff in, and then, there was some sort of a mapping exercise done. And here's another, I'll come back to this in a second. There's a consideration here. And then to Chris's point, on the back end, we were then transforming that into a MongoDB, and that's where we were actually doing the analytics. The analytics we were doing on MongoDB, and that was a whole other piece of software that, again, was in-house written in C++ and optimized to be really quickly. Now, we only needed to do this on a nightly basis. That was enough. We didn't need to do it like effectively real time. But we did need to recalculate everything on a nightly basis, for the reason being, because this was in the medical field, every day you're 1 day older. Right. So yesterday you were 49, today you're 50, right? And then different rules apply to you, different stuff kicks in. And so we had to recalculate everybody overnight. And we did discuss, being able to do it in a more smart way, where if you didn't cross over thresholds, we wouldn't necessarily recalculate you, but we never got to that point, sort of thing. So one of the things that I would advise is if you know that you need a data lake, get a data lake, right? Don't build one piecemeal haphazardly. And then the other thing that I've seen that might be interesting for you as well is I had attended some guy who was, he was basically their VP of IT for an online bookstore, and I forget what the name of it is. And they had an application out the front that did all of the ingesting for them, basically. I think it was Fivetran, if I remember correctly. And, its big thing was it just had a bunch of connectors, and it could pretty much connect to everything, right? And then suck it into your data lake for you. And then from there, they could do their own transformations, et cetera, et cetera. Now, here's an interesting consideration. I don't think this is something that you need to think about, but we needed to think about it. And that is, we actually needed to save effectively if you want to say the raw data, or at least some sort of representation of the raw data, because as I said, we would do these mappings, right? And these, kind of like you're doing, these enrichments where we would combine information. Right. But if we screwed that up, we needed to be able to go back, exactly, right? And then rerun it again, and then sort of say, oh, we screwed that up. Let's tweak the formula. Let's tweak the mapping, because the mappings weren't always just this field becomes that field. It was this field plus some sort of manipulation becomes that field. And if we didn't do the manipulation correctly, we may need to go back. And our requirement was we needed to potentially go back up to 2 years, right? Gotcha. To be able to do this, right? Because we were doing government reporting, HEDIS reporting, and potentially I needed to go back and restate the previous year's reporting if we found a problem, sort of thing. And so that's another consideration, is what's that intermediate format that you can keep around for 2 years that allows you to do those recalculations should you need to.
Right, but very helpful, Stephen. And actually, I would say that, yes, a lot of our needs actually sound very similar to at least what you just described. And we do want to keep, and we are keeping a copy of the raw data untransformed. And then later on, you need that middle layer. Right now, I think everything we do is AWS. So essentially, it's the S3 based data lake that we're trying to build. We're not there yet. We're still trying to get our raw data sources in order and trying to determine. It's just very elementary at this point. But overall, that's the direction. Yeah.
Well, and one thing that I have taken away from this book, speaking of that, is if I had to go back and do it again, I have become a really big fan of the Parquet format. If for no other reason than it embeds the schema in it. And over the next 2 years, as my customer changes the schema that they're feeding me, right, that's embedded in there. And if I then need to go back 2 years, right, I can reread that with less hassle than if I just have a CSV file from 2 years ago that I'm going to have to go and look at manually to see, can my reader still read it? Can I still process it, et cetera, et cetera? So there you go. I mean, that's one thing I would do differently based on the learning from this book.
Well, it has also the storage performance is much better than the CSV.
Sure, because it's it's column oriented,
Yeah, and it's denser. But so Becky, you know, I've heard between me, other people, we've commented, there's two sides to it, right? One is ingesting all this stuff. And so you can use some standard tools, data lake stuff, whatever. And then I thought I heard you talk about sort of combining information from different sources. And there's no magic bullet there, but what I will say is that combining different sources, so basically joins, that is the slowest part of any system. It doesn't matter in this chapter, you know, when they explained MapReduce, they spent some time talking about the different ways you could do joins. On Spark, joins is the slowest thing that you can do. And in a relational database, SQL Server, joins is what makes your query slow. So it is a fundamental problem that, you know, hopefully you have a decent programmer or engineer somewhere, you know, if you have two really large ones and you have to join them, that somebody's kind of thinking about this.
Have you guys come across any good solutions? Or is it just a matter of writing the code in the data engineering side?
Well, there's a trade-off you can do, which is denormalization, right?
Yeah, that's what I was going to say, but that's exactly our struggle. Like, either that I have heard recommendation of trying to be try to be selective, but still try to make your table or make maybe a big view or some sort. So those are pretty much the primary options on the table. Nothing.
I mean, I'm gonna sound, I feel like a broken record, but I don't know if it's this context or other contexts. A lot of it really depends on exactly what queries you need to do and what workloads you have. If you're doing a job and you only need to do it once to generate a report, or you only need to generate it once a month, then your data sizes, like your job finishes in 6 hours, that's totally fine for you. Then you don't necessarily have to spend a lot of time, you know, optimizing and engineering it. But when that changes, you need to be able to adapt it. So part of it is being able to develop a methodology of saying, okay, here's my data sources. Here is what questions I have. Here's what access pattern those questions kind of boiled down to with regards to what is coming from my data sources. And here is some either empirical or, you know, back of the napkin or, you know, estimated values for, will this job run fast enough for me to work with? That's really the thing that kind of comes into play. And, you know, everything depends on the size of the data you're using and whatnot. But like, I don't know, you know, that's I think what the technical side, you know, that's that's its job, like to try to figure out, is this going to work, or how do we make it so this does work? So that's really what you're trying to get people to work towards.
Yeah, I would echo that what Chris said. So it's how you're using it, how often you're hitting this stuff, how big it is, and how rapidly it changes. Right? So if you have, let's say you had consumer data on the entire country, so it's like 300 million records, and you only get it refreshed once a quarter. Well, like, okay, yeah, you could definitely run some sort of job, denormalize, match stuff, write it out. And even if it takes a week to run that job, you only need to run it once a quarter, you're done, right? Whereas if you were getting that change daily and you need users to be able to click, 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 hit that stuff, and they want, response time in a second or so, now you've got like a completely different problem. So
gotcha. And I agree that that's part of what we need to figure out. I think our situation is we don't need we don't require any real-time kind of reporting right now, and the changes to the data technically are not that frequent, like monthly, let's just say that. No, I used to say weekly to monthly, but I think where our bottleneck is, like, we need to run multiple of these kind of join queries very often, like to because we have we can have very high volume different projects, right? You have, let's say, 10 projects being needing to be done in 2 days, and all of the 10 projects require analytics that are coming from multiple gigantic tables. Like, for example, an example can be we're trying to combine people's click stream data. Like, okay, what kind of essentially their overall internet behaviors, like do they how often they shop, how often they watch entertainment, how often they go to travel content site, and their survey data, which also can be like multiple waves of survey data, so to speak. So we have a situation where you have 10 projects going on that 10 analysts are working on, or multiple analysts are working on, and all doing the same similar kind of join queries. And I think that's where we kind of really break down.
Okay.
Yeah, I've seen on my sorry that I cut in. Yeah, like there's at Visa we have like a consulting like data science consulting department, where it's like your case where different analysts have different projects and analyze for different companies, their transaction, consumers' behaviors. And what the solution for that team was that there is like a data science features warehouse where the data platform team would pre-process all different possible combinations for these intermediary features. For example, for what stores, how far is it, like maybe like 5 kilometers surrounding the store, how many consumers what kind of consumers were buying certain things, or what is the amount of spending in like near like 5 kilometers near where the store is located. So like they mapped out different kinds of intermediary features that are commonly reduced by different analysts, and then just store it there so people can retrieve those intermediary features for their own analysis. So they don't have to every single time go back to the original data, do all these computation joins, and like everyone, it doesn't have a standardized format. But I think it only makes sense if you do see this kind of mix and match happens a lot repeatedly in the foreseeable future. Right? If it is just one-time thing and the tables keep changing, then maybe it's not worth it. But then what happens was that for this particular team is that they always join on like the transaction table against other tables, then there's only that fixed kind of mix and matches that can happen.
Great to know.
Yeah. What I was going to say is that if your sources are fairly infrequently refreshed, weekly, monthly, then it sounds to me like, just at a very high level, from a cost effectiveness perspective, you can probably have certain kind of pre-computing that runs overnight. And that's going to be cheaper than buying some fancy new tool that does, you know, ELT and serves stuff up and blah, 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 you know.
Gotcha.
You know,
Very helpful.
If you said you have stuff that just changes every day, then that makes it a lot harder to do the pre-processing. It might be doable nightly. And if you have stuff that changes every hour, then you really need a tool, you know. But if it's monthly, just whether you call it denormalizing or just prepping or putting it into, like when he's saying a special feature store, whatever, but you can do a lot of pre-processing to lay it out, to index it, you know, to really just make it much readier, faster for use. And that just costs you a few bucks for disk space. It doesn't really cost you, you know, big dollars.
Hey, Becky, I have a question, and this is completely unrelated to what we're talking about right now, but you know how there's the new California privacy laws coming in? Yeah. If a consumer approaches you and says, I want you to purge all data related to me, is that even something you could possibly do?
Actually, I would like to ask the group these kind of questions. Like in my previous company, like the current company I'm with, right, we actually don't have any, I shouldn't say we don't have any direct consumer data, but at least we're not like a panel company. What I mean by that is that we don't directly kind of host and store a large group of people, like millions of people's data directly. In my previous company, like where I was for like close to 20 years, and I mean, for the GDPR and CCPA compliance, we do have to kind of get to a place where we show, yes, if someone requests that, we show the process of, okay, where we purge your raw data. The only the more difficult thing is the project level data, right? Like, because like you have hundreds and thousands of projects, how are you going to make sure this respondent IDs data is being used in some other projects? And then that's the difficult part. We can only say that, you know, I mean, to our clients, there's a year or 6 months kind of a storage time. If you guys no longer use it, we're going to just clean it. But I don't think there's and we have been looking for, like, is there a more global way to clean it out? The short answer is no.
I agree. I mean, my previous companies, we've never come up with a good solution to this.
Right.
So Stephen, thankfully, I don't deal with that now, but my last company, about a third of the contracts had written in retention policies where they wanted us to guarantee a certain amount of time, if they were no longer a customer or whatever, that this data would be destroyed. And then about a third of the contracts had data retention where they required that we maintain the data a minimum of a certain amount of time.
Yeah.
And then a third of them were silent. It's like, this is crazy.
They're
half
in conflict, right?
Say that we have to keep it at least this long. The other half of the customers are saying you can keep it at most this long. What? Okay, so just doing a quick time check here. Did so if we try to wind things down, did any other people have some final questions or discussion they wanted to have?